Today, we're tracing the literal journey of a light ray to understand exactly how we see the world around us. We interact with light every single waking second, right? But we rarely stop to think about the incredible physics and biology that actually make our vision possible. So we're going to take these concepts right out of the textbook and bring them to life.
Let's dive right in with a couple of everyday mysteries that the physics of light can easily solve for us. Have you ever glanced in your rearview mirror and noticed the word ambulance? Perfectly readable even though it's painted completely backward on the truck itself. Or what about looking up after a massive thunderstorm and seeing a perfect, giant arch of colors across the sky? Like, how does plain white sunlight just suddenly turn into a rainbow? Keep these questions in your back pocket because the answers are literally hiding in plain sight.
To get to the bottom of all this, we'll structure this explainer into 5 quick sections. 1. How we see light. 2. The rules of reflection. 3. Mirrors and splitting light. 4. Inside the human eye. And finally, 5. Vision defects and solutions.
Let's kick things off with Section 1, How we see light.
Imagine walking into a pitch-black room. You have perfectly healthy eyes, but in that moment, you're completely blind. Why? Well, because sight is basically a partnership between your eyes and light. The objects around us fall into 2 main camps. First, you have luminous objects. Think of these as the light bringers, like the sun, a lit candle, or an electric bulb. They actively emit their own light. Then you have non-luminous objects, like the book on your desk, a chair, or even the moon in the night sky. You only see these things because light from a luminous source hits them and bounces off right into your eyes. No bounce, no vision.
That brings us to Section 2, the rules of reflection.
Now, that bouncing back of light, it isn't just some chaotic scattering. It actually follows strict mathematical rules. Let's look at the geometry behind the bounce. When a beam of light hits a smooth surface, like a mirror, we have 3 key players. First is the incident ray. That's just a fancy term for the incoming beam of light. Then we have the reflected ray, which is the light bouncing back. And finally, right in the middle, we have the normal. The normal is just an imaginary line drawn exactly at a 90-degree angle to the surface, right where the light hits. It basically acts as our mathematical reference line. Armed with those terms, we can establish the 2 fundamental laws of reflection. The first law states that the angle of incidence, meaning the angle between the incoming ray and our imaginary normal line, is always absolutely exactly equal to the angle of reflection. So if a ray hits a mirror at 30 degrees, it perfectly bounces off at 30 degrees, every single time. No exceptions. The second law says that the incident ray, the normal, and the reflected ray all lie in the exact same plane. Imagine sliding a flat piece of paper straight down onto the mirror. All 3 of those lines would be drawn perfectly flat on that one single sheet.
And honestly, this brilliantly illustrates why you can see your face in a mirror but not in a piece of cardboard. With regular reflection, light hits a perfectly smooth, polished surface, like a mirror or totally still water, and the parallel rays bounce off parallel to each other. That gives you a clear, sharp image. But with diffused or irregular reflection, when parallel rays hit a rough surface like a bumpy wall or choppy water, those microscopic bumps change the angle of that normal line everywhere. So the rays bounce off in totally chaotic directions. You still see the wall, sure, but the scattered light prevents any clear image from forming.
Okay, moving right along to Section 3, mirrors and splitting light.
Let's see how these rules of reflection create the unique images we see every single day. When you stand in front of your bathroom mirror, which is a standard plane mirror, the image looking back at you has 4 very specific scientific traits. It's virtual and erect, which basically means it stands perfectly upright, not upside down. It's exactly the same size as you, and it appears to be at an equal distance behind the mirror as you are standing in front of it. You step back, your reflection steps back. But the coolest trait? Lateral inversion. That means the left side of the object becomes the right side in the image and vice versa.
And boom, this concept of lateral inversion solves our first everyday mystery. Emergency vehicles purposely print the word ambulance perfectly backward on their hoods. They know that when you're driving and glance up at your smooth rearview mirror, the mirror's natural lateral inversion will flip that backward text right side out. It lets you read the word instantly so you can get out of the way. It's literally utilizing the laws of reflection to save lives. Pretty awesome, right?
Now, what happens if we use more than one mirror? Well, by placing mirrors at specific angles to each other, we can bounce light back and forth to create multiple reflections. Take a kaleidoscope. It uses 3 mirrors angled at 60 degrees. As light bounces between them, it creates beautiful, infinite, continuously changing patterns out of little bits of colored glass. Fun fact, designers actually use these to brainstorm new fabric and wallpaper patterns. Then we have the periscope. By setting two parallel mirrors exactly at 45-degree angles inside a tube, light from the ocean surface bounces down the tube right into the eye of a submarine crew member, letting them see above water while staying completely hidden below.
So mirrors bounce light, but glass prisms can actually break it apart. This brings us to a really cool phenomenon called dispersion. See, sunlight looks completely white to us, but the truth is, white light is actually a hidden blend of 7 distinct colors. When white light passes through an angled glass prism, the light bends. And because each individual color bends at a slightly different angle, the white light splits apart into a beautiful band of red, orange, yellow, green, blue, indigo, and violet. You know, VibJor.
And this perfectly explains our second mystery, the rainbow. You don't actually need a man-made glass prism to see dispersion. After a storm, millions of tiny, spherical raindrops are left hanging suspended in the air. When the sun peeks out, those water droplets act exactly like tiny natural prisms. They catch the white sunlight, bend it, and split it into its component colors, painting that massive, stunning, dispersed arch of VibGR across the entire sky.
Let's shift gears to Section 4, Inside the Human Eye. We've tracked the physics of how light travels, bounces off mirrors, and splits through water droplets. Now let's explore the incredible biological machine that actually receives all this light. The journey through the eye starts when light hits the cornea, which is this tough, transparent, protective front layer. Next, it meets the iris, which acts just like a camera shutter to perfectly regulate the dark hole in the center, the pupil. The light then passes through the focusing lens, beaming the image all the way to the back wall of the eye onto a screen we call the retina. Finally, the optic nerve shoots that image as an electrical signal straight into your brain.
Let's zoom in on that retina screen at the back of the eye, because it is lined with 2 brilliant types of specialized nerve cells that process literally everything we see. First, we have cone cells. These are highly sensitive to bright light, and they are the magical cells that let us detect all those beautiful VibGR colors. Then we have rod cells. Think of these as your night vision workers. They are incredibly sensitive to dim light, allowing you to see shapes in the dark, but they cannot detect color at all. And that is exactly why everything looks kind of gray when you turn off the lights.
Fascinatingly, though, despite having millions of these cells, your vision isn't quite perfect. Right at the very back of the eye, at the exact junction where the optic nerve exits to head to the brain, there's a tiny area completely void of any rod or cone cells. If a beam of light happens to focus on this exact specific spot, your eye literally cannot sense it, but your brain just seamlessly fills in the background, creating a natural, invisible blind spot in your field of vision that you don't even realize is there.
Let's wrap things up with Section 5, Vision Defects and Solutions. So what happens when this incredible biological lens system struggles to focus? A healthy eye can comfortably focus on a distant mountain range and then immediately adjust to read a book held just 25 centimeters away. But sometimes the shape of the eye changes. The first common defect is myopia, or nearsightedness, where you can see nearby objects perfectly, but distant objects get super blurry. We correct this by placing a precisely curved concave glass lens in front of the eye. The exact opposite defect is hypermetropia, or farsightedness. Here, faraway objects are clear, but reading a nearby book is a real struggle. We fix this by bending the incoming light with a convex lens. So, by understanding the physics of light, we can manufacture eyeglasses that completely cure our biological shortcomings.
But human ingenuity doesn't stop at bending light. For those who are visually impaired and cannot process optical light at all, there are incredible non-optical aids. The most globally recognized is the brilliant Braille system, developed by Louis Braille. Instead of relying on light bouncing off ink on a page, this system translates letters and numbers into patterns of raised dots on thick paper. It allows visually impaired individuals to read and learn entirely through the tactile touch of their fingertips, completely bypassing the need for light altogether.
As we conclude this explainer, let's just take a quick moment to reflect on everything we've covered today. From the angle of a mirror flipping an ambulance sign, to tiny raindrops splitting sunlight into massive rainbows, all the way to the intricate cone and rod cells turning light into the colorful world we experience every single day. But remember our very first point, we only see what the light touches and bounces back to us. So I want to leave you with a final thought to spark your curiosity the next time you flip on a light switch. If our eyes are completely reliant on the light that bounces off objects, what else in the vast universe is hiding in plain sight, just waiting to be illuminated? Thanks for exploring the science of light with me. Keep wondering, keep learning, and I'll catch you in the next